All right. So good morning again, everybody. So welcome to week number 15, the final, I think, final week na ba? Hindi, meron pa pala tayong next week for the semester. But technically, this is the last module for Math 174, module number 11. And I think I also announced it that we won't have any any laboratory exercise left. So the last lab exercise 6, which is due on Monday, right before midnight, and so that means I won't have any laboratory exercise to test your understanding of module 11. So that brings me to the third problem in the problem set. So in problem set number 2, the third problem will be an implementation of Monte Carlo simulation, which is our topic for today. Okay, so ito yung pagandaan nyo for the third part. But I think this is pretty straightforward because this is an alternative to numerical quadrature formulas. Because numerical quadrature formulas, they have their appeal, ano? So, ang dali nilang i-derive, tapos nakadepende lang siya sa function evaluation of the integrand. So, we don't have to worry about closed form antiderivatives and other stuff, ano? Pero meron din silang ilang mga limitations kasi napaka-dependent niya on the abscissas used and on the abscissas used and the corresponding weights and or the available data. All right. And of course, since say for instance the Newton quadrature rules or the Newton Cotes quadrature rules, they heavily rely on interpolation theory. So they inherit the 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 difficulties, the shortcomings, and the bad things about the interpolation or interpolatory polynomials like the Runge phenomenon and so on. Tapos yung Gaussian quadrature, medyo mahirap i-derive yung mga mas matataas yung degree of precision, ano? So yun yung ilang mga bagay na gusto nating i-address in module number 11. Is there an alternative way to approximate the integral of a given function, all right? And what we'll look at is more of a non-deterministic or a probabilistic way of approximating the integral. Yun yung tinatawag natin na Monte Carlo simulations. It is non-deterministic or probabilistic in nature in the sense that when you run a Monte Carlo simulation, you will get a number, but when you rerun or you run the Monte Carlo simulation another time, you might get a different number because the x's or the abscissas that you're using is not uniform. All right? Hindi katulad ng Newton Cotes quadratures na pipili ka on the onset ng exabytes na gagamitin and then you plug it into your formula or you plug it into your interpolating function. And then you get an interpolating polynomial, then you integrate it, you're gonna get your estimate, ano? Sa Gaussian quadratures naman, predetermined yung mga exabytes. So one run of a Newton Cotes quadrature and or another run of Gaussian quadrature rule, they will give you one specific estimate. So Monte Carlo simulations, there's a sort of randomness in how the algorithm works. So that means when you run a Monte Carlo simulation on the same function, you might get different results every time. So that's why it's called probabilistic, and you will see later why. Okay, but here's what I want you to look at. At the end of the module, you should be able to discuss the idea behind Monte Carlo simulations and use this to solve scientific problems. Right. So let me just restart my my screen share for those who are having troubles. You know. Okay. Now, as I've mentioned, there is some sort of randomness here sa Monte Carlo simulation, but so meron siyang sense of randomness. So ibig sabihin, gusto nating gawin yung simulations either on a large set of data, all right, just to get the expected value. Yung mga nag-F mas dyan, nag-1 or actually nag-181 naman kayo lahat, ano? Tama ba? I forgot if BS Math students are still required to take Math 181. Pero ito yung parang expected value, all right? Or yung long-term behavior, because here we are working with randomness. So ibig sabihin, kailangan mong i-perform yung simulation on a large amount of data or do it sufficiently many number of times para mag-converge o maging stable yung estimate mo makukuha to a value, right? So it's basically an application of the central limit theorem or the law of large numbers from statistics, that if you have a random experiment, if you do it sufficiently many number of times, then you're going to get something that is close to the expected value. In this particular case, the expected value that we want to reach is the value of the integral, right? So here we go. Let's talk about Monte Carlo simulations. Well, Monte Carlo simulations is relatively new with respect to integration techniques. In its general sense, maraming ginagamitan ng Monte Carlo simulations, hindi lamang sa integration, but other probabilistic simulation processes are also called Monte Carlo simulations. So in a more generic sense, Monte Carlo simulations were born during the Second World War, where I do have their names here. It was developed by John von Neumann and Stanislaw Ulam during the Second World War, where they did some simulations to see what are the values of the parameters that they should use, say in designing rations of food or deployment of military assets, so that they can predict kung ano yung magbibigay sa kanila ng best outcome. So instead of deploying troops right away or implementing some operations right away, sinasimulate muna nila. Will this give us a good result? If not, they will try other parameters or different strategies. Tapos titingnan nila ano yung possible outcomes, and then they check which of those strategies will give us the best outcome. So ito yung mga silver lining ng World War, though nothing will condone the loss of lives during the Second World War, but there are really some the necessity during the Second World War spurred some technological advancements, even in the field of mathematics, katulad nitong Monte Carlo simulation. So basically, it's not deterministic or probabilistic, so it's a hit or miss routine. Ibig sabihin, it's either you get a very good estimate or you get a completely crap results, ano? So hindi katulad nung sa Newton codes at saka sa Gaussian quadrature that we have a specific idea how big the error would be. Sa Monte Carlo simulation, hit or miss ito. Either you get a good result or you don't. We don't have any control with it. Our only safeguard is to select as many data or to use as many data as possible. All right? Yun yung ating panlaban dun sa posibleng pagkakaroon ng miss nitong Monte Carlo simulation. And it's a hit or miss, so that means you gamble. So it's either you get a good result or not. If you're willing to take the risk, then do Monte Carlo simulation, because these are really efficient and they are very computationally cheap. And that's why, since it's a gamble between a hit or miss estimate, kaya pinangalanan siyang Monte Carlo simulations after a city in Monaco na sikat sa mga casinos. Kaya Monte Carlo simulations yung tawag niya. So here are some advantages ng Monte Carlo integration or Monte Carlo simulations over deterministic quadrature rules. Una, ito yung sinasabi ko kanina. It's very simple and easy to implement. But again, madali siyang gawin, pero it comes at a cost. Hit or miss. Wala tayong safeguards to ensure good approximate, except that we do the simulations either on a large data set or multiple number of times. Kasi ang theoretical basis niya lang talaga ay yung law of large numbers or the central limit theorem that tells us do an experiment or a random experiment sufficiently number of times, then you're going to get to the expected value. Okay. Now, another thing is that the method does not suffer from instabilities caused by non-smooth integrands. Kasi nakafocus ka lang talaga sa function value. So it is not hampered by the complexity of the integrand. Function value evaluation lang din naman yung ginagamit natin. Now, though kailangan mong gawin ng maraming beses yung Monte Carlo simulation, alright? Para mas malaki yung chance na magkaroon ka ng isang hit approximate, ano? Um, Ideal choice din ito sa higher dimensions. Actually, it gets better. Monte Carlo simulation gets better whenever you are performing it in higher dimensions, meaning you are integrating a function of many variables. Hindi siya ganon ka ang bagal kasi ng convergence ng Monte Carlo's integration. So hindi siya advisable to be used whenever you are in one dimension or two dimensions unless you can afford to use, say, a million data points or tens of thousands of data points. Pero if you go in the higher dimensions, actually, I think I will compute later. If you are in higher dimensions, which is really what happens in application. Pag marami ng variables yung functions mo, mas maganda ng mag-Monte Carlo simulation kasi yung order of convergence ng Monte Carlo simulation will be at par with with quadrature formulas kapag ka nasa mataas ka na dimension. I guess, or I think it's at least 6 dimensions. Pag nasa 6 dimensions ka na, meaning you're integrating a function of 6 or more variables, mas advisable ng mag-Monte Carlo simulation. Alright? So, yun yung, doon siya nagko-compensate pag mataas na yung dimension ng problem. Right? So, simple siya. And hindi masyado nakaka-apekto yung dimension ng problem. Halimbawa, i-compare natin to sa quadrature formulas. Yung quadrature formulas, napaka-dependent niya dun sa dimension ng problem. So halimbawa, you can only afford to use, say, 1,000 test points. So Monte Carlo simulation, it doesn't matter. You can use 1,010 points. That would be nicely spread all throughout the entire integration region. However, if you're using a quadrature rule and you are constrained to use only up to 1,000 test points, tapos halimbawa, nasa R3 ka, function of 3 variables yung ini-integrate mo. So pag nagka-quadrature formula ka, nasa 3-dimension ka yung domain mo, nasa R3 yung domain. So ibig sabihin yung X, Y, and Z components ay kailangan mong i-divide into just the 1,000 points that you need. So since you have 1,000 points na pwede mong gamitin, pero meron kang tatlong coordinate axis, you need to divide your coordinate axis into just 10 subdivision points. Kasi para yung total number of grid points mo ay maging 10 cube. So meron kang 10 subdivisions in the x-axis, 10 subdivisions in the y-axis, 10 subdivisions in the z-axis, tapos ilang possible triples yung makukuha mo? 10 cube, right? Kasi 10 choices for the x component, 10 choices for the y component, 10 choices for the z components, multiplication counting rule, magkakaroon ka ng 10 cube. So magkakaroon ka ng 1,000 grid points. Eh, ang numerical quadrature formulas nakadepende sa step size h, yung inyong error, yung theoretical error. So if you can only afford to divide each of the coordinate axes into 10 points, so ibig sabihin yung h mo ay 1/11 lamang on each of the coordinate axes, this value of h is relatively small. So ibig sabihin yung step size mo ay yung error ay nakadepende lang sa isang power ni 1/11. Okay? Not 1/11, 1/10 kasi siya yung H10 subdivision points nga pala yung ginamit ko. So that means magkakaroon ka ng magkakalayo na discretization points for your integral, and that's a bad thing, especially if you have a very complicated function, say a very oscillatory function. So ang laki nung epekto nung dimension nung ating integral problem doon sa subdivision natin into say a mesh of points para sa numerical quadrature formulas. Another thing is medyo mabagal nga yung convergence ng Monte Carlo simulation, pero yung error estimate sa kanya ay napakasimple lang. And this is basically a product of a simple application of the central limit theorem. This tells us that if you're using capital N data points, then the error in the Monte Carlo simulation is 1/square root of n. And it's easy to see. It's really simple, right? So if you wanna make the error smaller, ito ay isang multiple ni 1/root n. So you wanna use n you want to choose n to be a very large number, or you want to make n approach positive infinity. And then another nice thing is that that error bound is independent of the dimension of the problem. Kahit 5-dimensional, kahit 10-dimensional, or 6-dimensional yung integral mo, laging 1 over square root of n yung ating error estimate. Okay? Now, that could be a double-edged sword because napakabagal nga ng convergence ng Monte Carlo simulation. Ang error ay laging 1 over root n, right? So what you want to do is to use as large value of capital N as possible, regardless of the dimension of the problem. So tingnan natin, kailan magiging at par yung performance ng Monte Carlo simulation with a composite quadrature rule. Halimbawa, compare natin siya sa Simpson's rule. Now, Simpson's rule is a very fast converging algorithm. In fact, it's of order of convergence 4, meaning yung error ay proportional sa h to the fourth, right? So magkasing bilis nagzi-zero yung error at saka si h to the fourth, where h is a step size. So let's see, kailan makakasabay yung Monte Carlo simulation with the Simpson's rule or the extended Simpson's rule? Saang dimension? Well, recall that kung nag-integrate tayo sa isang unit interval, meaning an interval of length 1, and we're using little n subintervals, then ang ating h ay 1 over n. And the error mula sa composite Simpson's rule ay magiging proportional sa 1 over n to the fourth, right? Because again, the error sa composite Simpsons ay big O ni h to the fourth, h equals 1 over n, so that means the error is proportional to 1 over n to the fourth. And this extends to higher dimensions d. So if we assume that we are using n subintervals sa bawat coordinate axis sa composite trapezoidal rule, hold on. Parang nagulo yung script ko dito. Oh yeah, okay, that's fine. So if we're using n subintervals sa bawat coordinate axis, so gumagamit ako ngayon ng composite Simpsons sa isang function of several variables. So kung meron akong d na dimensions doon sa aking problem, so I have d variables, I will subdivide each of the d coordinate axes into n subintervals. So in all, I will get a multiple of n to the d na grid points. Or actually, kung nasa 2 dimensions tayo, ito ay mga rectangles, 3 dimensions, mga cubes. So basically, kung meron kang n intervals sa bawat coordinate axis, meron kang d na coordinate axis, so meron kang around n to the d points na ginagamit. Tapos sabi natin, kapag ka-composite Simpsons, so nakadepende siya kay h to the fourth. Pero si h to the fourth ay equal kay 1 over n to the fourth, where n is the number of subintervals used or the number of discretization points used. Pero kung nasa d dimension ka, yung capital N natin, the number of points that you used, is equal to n to the d. N is the length of each of the subintervals on each coordinate axis, and then d is the dimension of the problem. So here, if I will compute for n to the fourth, that means capital N should be 4 over d. Right? So dito lang, how do I get 4 here? Tama ba to? Yeah, because capital N is n to the d. So if I have n to the fourth, so that means that would be n to the 4d. Kasi yung n to the fourth ay number of points. Number of points to the fourth power, right? So that means here we'll have n 1 over 4 to the 1 over n to the 4d. Tama ba to? Yeah, I think this is right. So ito yung error constant dun sa Simpson's rule. Meaning, in a composite Simpson's rule, the error term is a big O of h to the fourth, But if you are in D dimensions, yung error mo ay magiging 1 over capital N raised to the 4 over D. Kasi si capital N ay number of points. So, i-raise mo siya sa 4 over D to get essentially what n to the fourth, little n to the fourth is. Okay. So, ito yung error bound o ito yung asymptotic error bound para sa composite Simpsons. Pero alam natin, para sa Monte Carlo simulation, asymptotic error bound ay 1 over root of n. So I'll just set the two guys equal to each other, composite rule. Tapos ito yung nanggaling sa Monte Carlo simulation. Solve for D, that means D is equal to 8. So that means na magiging parehas yung performance ng composite Simpsons rule at Monte Carlo simulation only when you are at least at dimension 8. So kung walo yung variables na ini-integrate mo, huwag ka na mag-composite Simpsons rule kasi yung performance ng composite Simpsons rule ay kaparehas na ng performance ng Monte Carlo simulation. And it might sound a stretch. Ang tagal pala bago makasabay yung Monte Carlo simulation. That's its big disadvantage. Ang bagal ng convergence ng Monte Carlo simulation. And empirical studies show na worth it na mag-Monte Carlo simulation, at least a simple Monte Carlo simulation, kapag ka nasa dimension 6 ka na or more. Well, probably from your point of view right now, sabihin nyo, ay bakit pa tayo nag-aaral ng Monte Carlo simulation? Eh halos lahat lang naman ang ini-integrate natin ay dimension 1 or dimension 2 or dimension 3 sa Math 38 no nag-multiple integrals na kayo, ano, ang konti lang ng variables involved. Pero sa totoong buhay, if you're modeling a natural phenomenon, ang daming variables na involved. Ang daming factors na nakaka-apekto sa isang bagay. Halimbawa, if you want to model the rice yield for your farm, halimbawa. So ang daming factors na involved. You have to factor in precipitation rate, average temperature, gust of wind, probability of extreme weather conditions, soil type, vegetation, ano pa ba? Availability of irrigation, etc. So ang daming variables na involved. So kaya sa totoong buhay, gamit na gamit yung Monte Carlo simulations kasi usually ang information mo comes in very huge dimensions, alright? Pero for cases when you are in the lower dimension range, pwede ka pa rin gumamit ng Monte Carlo simulation pero piliin mo na si capital N, the number of points that you're going to use to be very large in the first place. Probably tens of thousands or hundreds of thousands or millions if you can afford it. Okay? Now, promise ko kanina, napaka-simple nung implementation ng Monte Carlo simulation. So let's illustrate it using this integral, the integral from 0 to 1 of 1 over x squared plus 1 dx ng eksaktong value ay pi over 4. Right? So, una natin gagawin, I think I put, okay, mamaya ko pa siya sinummarize. So, idea ay pipili ako ng n abscissas over the integration interval. Alright? Pipili na ako ng capital N. So, in this simple example that I have in the slides, I chose n to be equal to 5. Right? Pumili ako ng 5 abscissas in random. Alright? So, I chose 5 random numbers that are uniformly distributed within my integration interval. Integration interval 0 to 1, pipili or bubunot ako ng 5 random numbers from them. Then what I'll do is I will calculate the areas of the rectangles with width b minus a and height f of x sub I. Right? So sa bawat isa dun sa mga x sub i's ko, kukunin ko yung area ng rectangle they represent. And I will call that each of them would be an estimate for the integral. Tapos ang gagawin ko, i-average ko lang yung 5 estimates na yon, and the average will be my estimate for the actual integral. Alright? So yun yung pinaka-idea na ng Monte Carlo simulation. So graphically, this is what happens. So here, this is the blue area is the one that we want to approximate, right? Because that's the area under the curve of 1 over x squared plus 1, right? And this is the x-axis. Ito yung hinanap natin na integral. Ang ginawa ko, Monte Carlo simulation, capital N equals 5, pumili ako ng 5 numbers at random from 0 to 1. And what I got from my random number generator ay itong 5 na ito. Now, I computed the areas of the rectangle, all right, from 0 to 1 dun sa integration interval. Tapos, ang height niya ay yung function value dun sa nabunot kong number. Right? So that means for say x sub 1, this is the rectangle that I got, right? The orange one. And that orange or the area of that orange rectangle is my first estimate for the integral, for the actual area. Okay. And then I will do this for all the other 4 points. And then you will see na on their own, yung mga rectangles, ang pangit nung estimate nila, right? Ang laki nung error dun sa estimation. For instance, x sub 1, or x sub 1 actually is a little bit good, ano? Kasi parang ito nagko-compensate para doon. Pero if you look at x sub 4, si x sub 4, in-overestimate niya yung area ng region. Kasi binilang niya itong portion na to, kasama siya dun sa estimate, pero hindi naman siya kasama dun sa original area. So merong overestimation na naganap kay x4. So x4 on itself is not a nice approximate to the integral. Pero if I will look at it in a larger context, I have another random number, x sub 2, all right? Ito yung nabunot ko na x sub 2, and this is the rectangle that I'll get from that x sub 2. Ang laki naman nung underestimate because that rectangle didn't include this blue portion, which is originally in the region, in the area of the region we are approximating, right? So basically, it seems that the estimate from the rectangle in x4 and x2 really compensates each other. So what I'll do now is I will get these estimates that we got, take their average, and I will report that average to be my estimate using the Monte Carlo simulation, right? So, yun yung ginawa rito. So, okay. So, dinescribe ko lang dito yung result. Ang pinakamagandang estimate ay relative error 3.96% lang. Pero, yung iba sa kanila, hindi ko na pala ni-report yung mga relative errors. Pero yung iba sa kanila, I expect to have very large relative errors. But if I take them on the average, sorry, ito na pala yung average. Nasaan yung results ko isa-isa? Hindi ko pala ni-report yung results sa bawat isang estimate or dun sa bawat isang random exabyte na pinili ko. Pero using the 5 abscissas that we have seen earlier, kinuha ko yung average nila. What I'll get is 0.754291 with relative error just 3.96%. And that is good for some application areas. Usually, ang target mo ay 5 to 10% error. Pero rito, we got 3.96%. At how many operations? We only did 5 function value evaluations and then taking the average of them. Napaka-cheap ng computation natin ginawa. Meron ka lang 5 random numbers, kinuha mo yung area ng mga rectangles using the length of the interval as the width and the function value as the length. Tapos in-average lang natin, voila, we got 3.96% error. Now you can make it better if you increase the number of draws or the number of points used. Pinaglaruan ko yan. Yung ginawa ko. So A sabay ay yung area ng bawat rectangle. Isang rectangle lang yun, no? So area ng bawat isang rectangle na nakadepende doon sa iyong mga random numbers na napili. Tapos in-average ko lang, kaya may multiplier dyan ng 1 over n. Pag isang point lang yung ginamit mo, x sub 1 lang at 1% yung error. Tapos pag sinamba ko na si x sub 2, 15% yung error, medyo lumaki. Sinama ko si x sub 3, so ganito ko siya ginawa. Kunwari si x sub 1 muna, tapos si x sub 2 muna, si x sub 3 muna, si x sub, si x sub 1 muna, ito yung n equals 1. Tapos yung n equals 2, si x sub 1 at saka si x sub 2, kinuha ko yung average nila. sa n equals 3, si x1, si x2, at saka si x3, kinuha ko yung average nila, and so on. Yun yung nandito sa table na to. So error, pag isang point lang yung ginamit ko, 1%. 2 points, 15% error. 3 points, 10% error. 4 points, down to 1% error. And then 5 points, 3.96% na. So, ito yung progression. Pero usually, hindi natin to ginagawa. Kasi hindi tayo nagsisave ng random numbers o yung mga results sa bawat isang random number. So usually, pipili ka na kagad ng ano yung capital N. Tapos, magdodraw ka na ng capital N random numbers, tapos magmo-Monte Carlo simulation ka na ulit. That's how it is usually done. Pero itong nasa figure 11.3 o table 11.3, gusto ko kasing i-observe ano yung epekto na nagdadagdag ako ng points. So, halimbawa, dito sa n equals 10, ginamit ko yung unang 5 draws na nagamit natin. Bumunot lang ako ng 5 additional points para mabuo yung n equals 10. Tapos yung error niya na ay 4%. If I add 10 more random numbers to my already existing 10 random numbers, I get 20 random numbers. The average area of the rectangles will be 0.72 and so on. That's 8% error. And then I continually increase the number of points that I'm using. Now, at the point when I have 10,000 random numbers or random draws, the relative error is now at 10 to the negative 4. Napakalaki na nung improvement, right? And if I do 20,000 points, I can further reduce it to 1.0206. So really, kung makikita nyo, parang napaka-erratic nung behavior kapag ka maliit pa si capital N. Nagfa-fluctuate. Mataas na relative error, lumiliit, tumataas, lumiliit, lumiliit. And that's due to the probabilistic nature of the Monte Carlo simulation. So ibig sabihin talaga, para magkaroon ka ng isang stable estimate to your integral, kailangan marami kang points na gamitin. And you see here at the 10,000 point mark, we get relative error less than 1%. No? So ito ay 0.03% na yung relative error. Okay? And that's it. Yun lang yung Monte Carlo simulation. So pwede na nga tapusin natin yung lecture today. So ang idea, bubunot ka lang ng mga random numbers, kukunin mo yung area ng rectangle corresponding to that random number, and then take the average. But you should be guided on the choice of capital N. Remember that the error in the long run is proportional to 1 over square root of n. In this particular case, I got lucky with my draw. All right? Kasi masyado nang maliit yung relative error ngayon. Kasi kung susundin ko yung relative error estimate, sa 20,000 points, yung error dapat ay may factor na 1 over square root of 20,000. So that's about 7 times 10 to the negative 3. But we got a slightly better result, 1 times 10 to the negative 4. So it's about 1 order better than what was the expected relative error. Okay, so any questions, guys, so far? I hope the method is clear. Huwag niyo munang isipin na paano kaya ito kayang pahirapin ni sir, kasi nagdududa na po kami, may trust issues na kami, sir, na hindi pwedeng ganyan kasimple yung ipapagawa mo sa amin. But essentially, that's just that's Monte Carlo simulation. That's that simple, ano? Sige, tingnan natin yung mga variations ng method, ano? Okay, but before that, let me summarize what to do, ano? So una, select a value of capital N, right? So total number of points of random numbers to be used. So remember that the error will be proportional to 1 over root n. So that will guide you kung ano yung capital N. Pero gusto mo yung capital N malaki, right? That's the essence, ano? Then second, you draw a sample in your space omega, right? So si omega kahit ilang dimension yan. So r to the d. So kung nasa 2D ka, nasa 3D ka, pipili ka ng n random points. So kung nasa 2 dimensions ka, pipili ka ng capital N ordered pairs dun sa xy axis. Kung si d ay 3, so ibig sabihin si omega ay isang region. Yung integration region omega mo ay isang region sa R3. So ibig sabihin, bubunot ka ng capital N na mga ordered triples. So sa three-dimensional space, pipili ka ng capital N random points. Okay? Tapos, kukunin mo lang ngayon yung average nung, kasi kukunin mo yung, extend ko na to ngayon, no? Hindi na siya rectangles lamang. Pero kukunin mo yung volume using the area of omega or the size of omega times the function value. Kasi kanina, ang ginagawa natin ay 1 over n summation ng area, okay, ng mga rectangles. Pero ano yung areas ng rectangles? It's length. So this is the length of your interval times function value. All right, at that particular random point. Ano yung length nung ano yung length nung rectangle o yung width ng rectangle? That is simply the length of your original interval. So ano lang siya, b minus a. Tapos pwede ko na pala itong i-factor out yung b minus a, lalagay ko na lang siya dito. Okay? So matitira ito. So ito basically yung formula na ginamit natin kanina. Length of the interval all over n times the summation of the function values. Area ng rectangle. Average areas ng mga rectangles. So, pero itong b minus a, ito ay yung size ng integration interval. Alright? Now, kapag ka nasa higher dimension na tayo, nag-i-integrate ako over omega, the size of omega will now be generalized. Hindi na lang siya length ng interval. So, pwedeng si omega ay area na ng integration region kung nasa 2 dimensions ka. Kung 2-dimensional yung integral mo, kukunin mo yung size ng integration region. Kung saan ka nag-i-integrate, tawagin mo yung omega, kunin mo yung area ni omega, yun yung papalit mo sa b minus a. Tapos, over n pa rin, which is the number of points, times summation ng mga function values on the randomly chosen abscissas. Now, if you're in 3 dimension, b minus a will be replaced by the volume of omega. Tapos pag nasa 4th dimension ka na, 5th dimension, and so on, volume pa rin yung tawag natin dun sa size ni omega. So essentially, it is the size of omega divided by capital N times the summation of the function values. But essentially, ito pa rin yung idea na kinukuha natin yung average volume no integration region na may added dimension or added height, which is given by the function values on each of the exabytes. All right? So don't worry, mamaya may example tayo ng nasa 2 dimensions yung omega. All right? Para mas ma-visualize niyo siya. Pero balik tayo dun sa 1 dimension muna. Probably yung 2-dimensional ay sa Friday na. And probably I can share with you a MATLAB code for Monte Carlo simulations, at least the one that I drew. All right? Simpleng program. Okay, halimbawa, weekly example. Halimbawa, ito yung function natin, x times sine x cubed. Now, in this particular case, hindi advisable na gumamit ng quadrature rules, especially if you cannot afford to use many points, because the function f is highly oscillatory. You see that it wiggles a lot. And if h is not small enough, if your step size is not small enough, then you won't be able to capture the oscillatory behavior of the function f. Halimbawa, 5 points lang yung 5 equally spaced points lang yung kaya mong gamitin. Or halimbawa, 4 para tama. Kung 5 equally spaced points lang yung kaya mong gamitin, mag-start ka kay 0, mag-start ka kay 1, tapos kay 2, tapos kay 3, tapos kay 4. Alright? Now, kung yung 4 ay yung 5 points lang na yan, yung gagamitin mo sa isang Newton-Cotes quadrature o sa Gaussian quadrature rule, you'll be doomed to fail because look at this. Hindi nakaka-capture ng data points mo yung oscillatory behavior ng function f. Hindi mo malalaman na, oh, there are times pala na yung function value ay nasa ilalim ng x-axis. And that is very crucial in integration, right? So, ang nakikita lang halimbawa ni Newton-Cotes quadrature, gumamit ka lang ng 5 points, posibleng ito lang yung nakikita niya. Alright? Kung polynomial man yan. Yan lang yung line na yan, yung itatry niyang i-integrate. So, you are losing information because the value of h is not small enough to capture the oscillations of the function. But if you increase the number of points that you're going to use, you will have very complicated quadrature rules, right? So magde-derive ka na, magkakaroon ka na ng halimbawa 100 points yung gagamitin mo. So kailangan mo kunin yung degree 99 interpolating polynomial tapos yun yung i-integrate mo, alright? Or kung sa Newton-Cotes formulas, kailangan mo sa Gaussian formulas, kailangan computein mo yung abscissas at saka weights so that you'll get 199 degree of precision. And that's hard to do, right? So dito papasok yung advantage ng Monte Carlo simulation, even if we are in dimension 1 or we're integrating a function of a single variable. Now, I have several instructions here, right? Tingnan na lang natin yung results. Una, pinapagawa daw ay 100 sample points. Okay. 100 sample points, pag gumamit ako ng 100 sample points, ang makukuha kong estimate ay 1.017 with relative error of 284.23%. And that's not very good, kasi almost double yung error. Now, the caveat here is that I only used 100 points, and Monte Carlo simulation is really hit or miss. And I guess in this first simulation, I had a miss, all right? Yung pala, pag tinry nyong i-recreate itong examples dito, hindi nyo makukuha eksakto kung ano yung mga nakuha kong figures dito kasi nga probabilistic to, so depende ito dun sa random numbers na na-generate nyo. Pero if you want to investigate, why did I get 284% error when I use 100 points? Pwede nating ipag-graph si F kasama yung sample points in one coordinate axis. And here's what I got. Now, medyo okay siya kasi meron tayong mga nakuhang information about the oscillations, but that seems to be not enough because we got 284% error. And one thing that I noticed is that kasi uniformly distributed yung random numbers natin kinukuha, so they are designed to be picked at random, but at very nice intervals. So hindi sila magkukumpulan kasi uniform random nga yung distribution ng mga random numbers na yon. So ibig sabihin hindi sila possible na magkumpul-kumpulan dun sa interval 0 to 4, right? Equally spaced sila. And I see here that, okay, ang dami kong masyadong points na na-allot dito sa portion na wala namang masyadong action na nagaganap, right? So this is a pretty behaved part of the graph wherein I could afford not to give too much points at this particular interval. So baka yung konti na lang ang i-draw ko na points dito sa interval na to, tapos dito ako pumili ng mas maraming points. Yun yung parang adjustment na gagawin ko. Sa Gaussian quadrature rules, you cannot do that kasi sa Gaussian fixed dapat yung mga exabytes. If you want to do it sa Newton-Cotes quadrature formulas, kailangan mong i-redo yung computation. So medyo expensive ulitin yung sa mga quadrature formulas. Pero kapag ka Monte Carlo simulations ka, okay, posible kang pumili ng adaptive drawing. Halimbawa, dito muna ako pipili ng, halimbawa, 10 points lang, tapos dito ko i-alat yung 19 points para mas ma-capture ko yung behavior ng oscillations. So that's another thing, pero I just realized yung palang pala yung number ano ba yun? Yung palang pala yung number 4. Meron pang dalawang numbers na nauna or dalawang questions na nauna. Yung second question, pinarami lang. 25,000 points yung pinagamit. Alright? So 25,000 points yung pinagamit. Ang nakuha kong sagot ay ito. 17% error. So 100 points, 284% error. Now I increase the number of points 250 times. So nasa 25,000 na points na yung ginamit ko. 17% na lang yung error. And you might be saying, parang ang unti pa rin yung improvement kasi 250 times yung random numbers na pinili ko pero from 284, naging 17% pa lang sila. And 17% is not usually a good error. So kailangan mo pang lakihan yung number of points. Ganun. And here, this illustrates yung kabagalan ng convergence ng Monte Carlo simulation sa one dimension. Alright? Kasi nga, gumaganda lamang yung convergence ng Monte Carlo kapag ka either marami ka ng points na ginagamit or nasa mataas ka na dimension. So kahit tinaasan na natin yung number of points, medyo mabagal pa rin yung pagko-converge niya to the true answer. So nasa 17.68% pa lang tayo. Now, on Friday, I'm gonna show you two more ways or two more tricks on how to improve the results we got from the Monte Carlo simulation. Ano? Una, yung use of several Monte Carlo simulations. Kung ang kaya lang ng RAM mo talaga ay 25,000 random points at a given time, that's fine. We can do several Monte Carlo simulations and then just average out the results that we got from each. And hopefully one of those will be a hit, all right? Or most of them will be a hit that will give us better estimates. Or yun nga, the other trick is to use a stratified sampling of the random points depending on how the function little f looks like. All right. So yun yung titingnan natin on Friday together with an illustration of how to do Monte Carlo simulation in 2 dimensions. Okay. So I'll stop here. Do you guys have any questions or concerns? All right. So if there are none, then thank you guys for joining me today. Let's still see each other on Friday. And then, yeah, attend pa rin kayo kasi yung Monte Carlo simulation, ito yung number 3 doon sa problem set number 2, which hopefully will be available before the weekend. So either today, tomorrow, or Friday. Para sure. So, but definitely by Friday, it should be available. All right. So have a good one, guys. See you on Friday.
Thank you, sir.
All right. You're welcome.